All right, how's it going, everyone? So this is a video about the last summative of our year, the roller coaster summative. All right, in this one, we're investigating how energy changes as an object has motion. Right? We're also going to talk about the law of conservation of energy, that idea that energy is never created or destroyed, it simply transforms from one form to another. Now, if you did not do this assignment in class, what we're doing is we're building a roller coaster and analyzing how much energy our coaster has at each point in the track. Now, our first step in here is we want to look at how to build our roller coaster. So we're actually going to be using this simulation right here. So if you're on your computer or your device, you want to go ahead and type that link in so that you can have access to the roller coaster builder. All right. Before we get too far into it, we are talking about energy, and in particular, the two types of energy that we're focusing on are gravitational potential energy and kinetic energy. So this is a point where you want to make sure that you are defining these two terms in our pre-lab questions. Again, if you don't really have an idea of how to define them, what you can always do is you can define them in terms of an example, right? What might be an example of when an object has gravitational potential energy? What might be an example of when an object has kinetic energy? All right. Having done that, we go into our procedure of building our roller coaster. So our goal is to build our roller coaster using our materials following this design. We start with a large starting hill that goes down towards the ground, goes into a loop-de-loop, over a hill, and then back towards the ground. So once again, in building this roller coaster, we can use this link here to do this virtually. I'm going to pull up what the link looks like. And you'll see when you click on this link or you type it in, you'll get to a page that looks like this. We want to use the playground feature. Okay. And in here, we'll be able to build our roller coaster. So we can grab our tracks, and we will start by building a large starting hill, a little loop-de-loop, and then a second hill. Now again, you can change the height of the loop-de-loop, your starting height, the height of the second hill. All right, you can kind of arrange that however you like, but it should just follow this general format. All right. Back to our assignment. We want to start with a hypothesis. Our hypothesis is asking, how do we think the shape of the track will affect our rider's speed? All right, so really what this is asking is like, if we make the starting height taller, right? If you start with a larger ramp, right, will our object go faster? Will it go slower, right? If we change the height of the loop-de-loop, will that cause our rider to go faster? Will it cause them to go slower, right? So kind of answer that for yourself in the hypothesis. The next section we're looking at is the length of a roller coaster. This is when we have to do some measurements. Now, it's a little bit tricky in the simulation, but there is a way for us to do it. So what we're going to do here is we head back to our simulation. You'll notice that we have our little tape measure here in the bottom right corner. So because our roller coaster is not one straight line, we do need to kind of break this up into a few different parts. It kind of helps to be writing this down on, kind of a blank part of your paper, or do this on a separate sheet of paper, because we're going to have to actually add up kind of each straight section of our track to find out the total length. And this is how we're going to do it. So I'm going to take... Another way you can do this is just have your calculator ready on your phone or other device. I'm going to take this, I'm going to take the starting point of my measuring tape, put it at the start. I'm going to take the other end, I'm going to drag it down to kind of create a generally straight line here. We are going to do a lot of estimation. So I see that this section is about 7.6 meters in length. I'm going to bring it down to where I had it. Do the next kind of general straight section. Okay, plus 4.5. Okay, plus 3. Again, this is a very rough measurement. Plus 3.8. Plus 5. Plus 3.7. Plus 1.7 equals. So for me, when I added all those up, my total is about 29.3. Make sure you are doing your own measurements. I'm going to be putting some numbers in here as an example, but your numbers should be different than mine. Maybe not that much different, but what I don't want to see is I don't want to see just numbers that are copied. All right. Next, what we want to do is we want to measure how long does it take our rider to go through our entire track. So we're done with our measuring tape. Right, put that over here. What we want to do is we want to time how long our rider takes to go from the beginning to the end. We do have a little timer here next to the measuring tape. I'm going to take that out. What I want to do is I want to time, right, how long my rider is going to take to go from beginning to end. Now, to do this, there's a pretty easy way to do this. You notice at the very bottom of the screen, we have a pause button. I'm actually going to start by hitting that. And then I can hit the play button on the timer that's up here. Now, when I click restart my time, restart skater, you'll notice that they'll start at the beginning, but they're not moving. That's because we have not hit the play button at the bottom. You notice that our timer hasn't started yet because we have not hit the play button. All right. The key thing is I want to make sure that I stop the timer, right? I stop this when my rider gets to the very end of the track. So I'm going to hit this play button down here at the bottom, and then I'll hit the pause button again once we get to the end of the track. So play, going through, going pause. Okay, about 3.7 seconds. Okay, so I'm going to record that here. All right, to reset this, I'm going to hit the arrow on the timer to reset the time back to 0, and I'm going to hit restart skater. Notice that they go back to the same spot that we had them. Going to hit the play button. Well, first I want to make sure that I hit the play button on the timer. All right, that won't get the rider moving, but it will start the timer when we actually make them move. All right, now I can hit the play button at the bottom. Go through. Look at that. 3.7 again. We do it one more time. Now for you, you want to do this 5 times in total. I'm only going to do it a few times just to kind of show you the general process. Okay, not as exact that time. That's why we do multiple trials. All right, so make sure that you guys also do the 4th and 5th trial. And then what we want to do is we want to find the average time, because what you get is you get 5 different times. They should all be pretty similar. Some of them will even be the same, but we want to be sure that we are averaging them to get the most accurate time possible. So anytime you want to find the average of a number, you add up all the numbers that you have. So what I'm going to do here to find my average is I'm going to add up all my numbers I have. All right. And then you divide that total, that sum, by how many numbers you have, right? So for me, I did 3 trials, so I'm going to divide this by 3. But if you do 5 trials, right, you fill out trial 4 and trial 5, which you should, actually you need to, you would divide it all by 5. Right? And then also add the 4th and 5th trial in there. So for me, I'm going to do 3.7 plus 3.7 plus 3.73 equals 11.13 divided by 3 equals 3.71. So on average, it took my skater about 3.71 seconds to go from beginning to end. Once again, make sure you are recording your own times and calculating your own average. Don't just copy the numbers that are in this video. All right, for the average velocity, if you remember, velocity is distance divided by time. Now, we measured the total distance of the track, right? How long it is. For me, I got 29.3 is the distance. And you calculate the average time. For me, my average time was 3.71. So to find my velocity, I do distance divided by time. I'll see that my rider was moving 7.89 meters per second. They're moving pretty fast. Okay, next thing I want to look at is okay, what is the height of my roller coaster? And what is the mass of my rider? Okay, I'm done with timing, so I can actually take my timer, put it back in the toolbox over here. And now that I want to be looking at heights, what I can actually do in the bottom left corner, you'll see there's a section that says grid. If I check that, it brings up this grid here. Now, this grid is really useful because it just gives me a reference for how tall the track is at each point. So the very bottom, obviously, is our 0, and each of these lines represents 1 meter. So my starting point is about 7.5 meters. All right. So highest point, I'm going to say 7.5 meters. Okay. In our classroom, we use a marble for our rider, but for the virtual version, right, it's a skater. And the nice thing about this is you can actually change the mass of your skater. If you look at the right side of the page, kind of towards the middle where it says mass, by default, the mass of your rider is 60. All right, you can actually change that if you want, but by default, the mass is 60. All right, and then you can give your roller coaster a name. Now, what I want to do here is I want to get into the analysis of my roller coaster. So, I have 5 different sections of this, right? I have the starting point, the ground before the loop-de-loop, the loop-de-loop itself, top of the hill, and back on the ground. Now, what I want to do is I want to record the height of each of these positions. So, position 1, I already recorded that, right? The height is 7.5 meters. At position 2, before we go into the loop-de-loop, right, kind of when my rider's here, notice that this is basically on the ground, so I'm just going to call that 0. Okay. Top of the loop-de-loop, I'm going to say, just to round this up, I'm going to say it's about 4 meters. Okay, position 4, top of the hill. Gonna round this up right when they're about here. I'm just going to lower this a bit. I'm going to say that's 3 meters. And then position 5, they're back on the ground again, so the height is 0. Okay. Now, what I want to do is I want to look at potential, kinetic, and total energy. We're going to start by calculating the potential energy of all of these, because if we remember from our class, potential energy is a measure of potential energy is a measure of the energy an object has due to its position, right? So when an object is sitting flat on the ground, it has no potential energy, right? But when you raise an object off the ground, you'll notice that when you drop it, it will begin to move, right? Because it has stored energy due to gravity. So potential energy, if we want to know how much energy an object has, we need to know the mass of the object. The more mass it has, the more energy it's going to have, okay, times the gravity of the planet it's on, right, times the height or position that it's being held at. Now, luckily, on Earth, the gravity or the gravitational acceleration is always going to be 10. So I'm going to just replace that g with a 10. So as long as you know the mass, you'll multiply the mass by 10 and multiply that by the height. All right, so for position 1, I'm going to do the mass times 10 times the height. Now I know that my mass is 60. So I get 60 times 10 times my height, which at position 1 is 7.5. Okay, so 60 times 10 times 7.5. And we get a pretty large number. I get 4,500 joules. All right, it's that mass times height times gravity. Now, notice at position 2, and this is going to be the same for position 5, my height is 0. Right? Now, if I remember from just basic math, anything times 0 is always just going to be 0. I'll just rewrite this a little bit clearer. We have mass times 10 times height again. 60 times 10 times 4. That should be 2,400. All right, you can fill out the rest. All right. Now, key thing here, position 1, before we drop our object, right, our object's not moving, right, our skater is just kind of hanging out, right? So position 1, before they start moving, they have 100% kinetic energy, 100% potential energy, but no kinetic energy. All right, so at position 1, their kinetic energy is going to be 0. Now remember that total energy is always going to be potential plus kinetic. So, in order to find total energy, we add potential to what we have with kinetic. That gives us our total. So in this very first position, I have potential energy of 4,500 plus 0 is obviously going to equal 4,500. Now, one thing that's worth looking at. Now I'm going to I rearrange this so it becomes easier to see. What I want you to do is I want you to take a look at the energy bar as the skater goes through. Notice we have potential and we have kinetic and we have the total energy. As the skater is going through, notice what's happening to the total energy, that yellow goldish bar. All right. Is it changing? You notice that it's not, right? It's staying the same. This gets us back into the conservation of energy. Energy is never created nor destroyed. It just transforms from one type to another. Now, if we pause our skater at any point in this roller coaster, you'll notice that if we take the green kinetic bar and put it on top of the blue potential bar, we're going to get a bar that equals the total energy. Right? That's just showing us that potential plus kinetic equals the total amount of energy. All right. Kind of no matter where it's at. Yeah, even the points where we have 100% kinetic and no potential, right? When we add those two together, it's still going to equal the total. What that means is our total energy never changes. So since we had a total energy of 4,500 joules at the beginning at position 1, that means it's going to be the same amount at position 2 when they're on the ground. It's going to be the same amount when they're at position 3 when they're at the top of the loop-de-loop. Same amount when they're at the top of the hill. Same amount when they're back on the ground there. All right. Now, we talked about that total energy equals potential energy plus kinetic energy. Now you notice here, right, with kinetic energy, there's a formula that we can use to calculate it, but there's actually an easier way. Right, since we already know what the potential energy is going to be and we already know the total energy, what we could do is we can just take our total energy subtract the potential energy, and that will actually give us kinetic energy. Right. So for example here, we have 0 potential energy plus something equals 4,500. Or we could do 4,500, which is our total energy, minus 0 equals blank, right? 4,500. Which should make sense because at position 2, our rider's basically on the ground. Okay, and notice as you get closer to ground, potential energy gets less and less and less and less and less. And then the moment that they're on the ground, they have no potential energy, 0, because the height is 0, which means all that energy converted into kinetic. Okay. So use what you learned here to fill out the remainder of this table. These last 3 questions are pretty straightforward. Again, make sure that all the numbers in your document are yours and your own. They should not match the numbers that I have here. They may be close, but they should not be exactly the same numbers. All right, if you have any questions, please feel free to send me an email, but make sure that you have watched the entirety of this video. Thank you.